So hi guys, I'm Raghav, and in this video we will discuss the first four problems of Codeforces Round 960. So let's start on with the very first problem, submission bait. So the problem says that Alice and Bob are playing a game in uh, where they are having an array of size n. So they take turns to do operations with Alice starting first. In one operation, okay, so they have told that the person who cannot make any operation will lose, and at first there is a variable mx which is set to 0. So in one operation, the player has to choose an index such that the element on that index is greater than or equal to mx, and then set mx equal to ai, and then ai will be set to 0. And we have to determine whether Alice has a winning strategy or not. So it's like there is an array. The elements of the array can be anything in the range from 1 till n. It doesn't really matter, and n is very small here. So uh, there are two players, Alice and Bob. They will play alternative turns, and Alice is gonna be the first one to play. So initially there is a variable mx which is equal to 0. Now let's say if the values of the array are 3, 7, maybe 2, 1, 4. Let's say that there is an array 3, 7, 2, 1, 4, 6, 5, anything. So Alice wants to make sure that he is able to play a move, and after that, Bob should not be able to play a move, or like whatever happens at the end of the day, Bob should be the one who cannot make a move. So here, I think it's quite obvious that if you choose the largest guy in the array, that case mx will become equal to 7, and this guy will become equal to 0. Basically, Bob will not be able to choose this element anymore. So in that case, Bob will have to choose any other element which is either equal to 7 or greater than 7. And since we have chosen the largest element, and like in this case, there is no other element which is greater than or equal to the current element, so Bob will not be able to make a move and Alice will win. Right. This is the first thing which we should have in our mind. This is the very simplest case we can think of. Now, this is not really correct. Try to think about it on your own. Maybe just pause the video and try to think of a case where like Alice might not win on the very first move. In this case, Alice just made one move and Bob was not able to make any move. Try to think about another test case where Alice cannot win in just one move. So I hope that you pause the video and try to think about it. So let me just give you an example. Maybe if the array is something like um, 2, 4, 4. In this case, even if you choose the maximum element, Bob will still have some other element to choose. So choosing either one of these fours will actually make sure that Alice will lose, because Alice will make a move and then Bob will choose the another four. Now both of these would have been set to 0, and Alice will have to pick up an element, but there is no other element greater than equal to 4. So Alice will lose. Now I think it's quite obvious that in this case, if Alice had chosen this 2, in that case Bob would have to choose one of these fours, and we know like whoever will choose the first four, like let's say Alice had chosen this 2, then Bob chose this 4, then Alice can choose this 4 and Bob would not be able to make any move. So in this way, Alice could have won. So can you try to think of, can you try to generalize this? Can you try to think of some constraint on the frequency of the maximum element through which you could decide whether Alice will be able to win or not, or whether Alice will definitely lose or not? This is something you should actually like definitely try. Pause the video and try to think about it on your own. So the thing is, let's say if the maximum element here, that is 4, If it is coming only once in the array, in that case, allies can just pick up this 4 and win. It's true for any value. Like as soon as the maximum element is coming one number of times, allies can definitely win. If it was coming up two number of times, allies still won, but there was no guarantee whether allies would win or not. Let's say if 2 was not there in the array and there were only two elements, then Bob would have won. So yeah, we know that if MX is coming up two number of times, we don't really know whether allies will be able to win or not. Let's say if the maximum element is coming up three number of times, maybe the array is something like 7 7 7 and then 2 4 6 whatever. Like we don't really care about the rest of the array as soon as all the elements are less than 7. Allies can just pick up 7. Bob will obviously have to pick up 7, then allies will pick up the remaining 7 and allies will win because Bob will not be able to make up any moves. So yeah, if the maximum element is coming up odd number of times, like this is what we can conclude, that if the maximum element is coming up odd number of times, allies can just pick up the maximum element in the first turn and then Bob will be forced to pick up the other element and it will go on. And at the end of the day, uh, allies will be in a situation where Bob cannot pick up an element. It's because if there is some element coming up odd number of times, allies picked one, Bob picked one. Now it's again allies turn and there will be again odd number of elements left. So at the end of the day, it doesn't matter how many sevens were there at the beginning. At the end of the day, there will be only one seven left, which allies will pick, and Bob will not have anything to pick up. So, yeah, if the maximum element is coming up odd number of times, the winner is allies for sure. And if it is coming up even number of times and allies picks up the maximum element, he's lost. I know we have seen this thing. So, allies will definitely not pick up the maximum element. But can you try to think of what other element allies should pick? Like he obviously cannot just go up and pick up any random element. Try to think of what should be a live strategy now. Now that we have figured out at least this much, that you want your opponent to have even number of elements left to pick up from. So if there is something like 2 2 2 3 3 and maybe one as well. In this case, allies can just pick up one of, like you know that if allies goes up with any of these threes, then allies will be lost. So he will definitely try to avoid it. He would want that allies picks up one of these elements and eventually Bob should be forced to pick up one of these elements. And then allies can just go on picking up the other one and eventually Bob will lose. So in this case, uh, like allies can either pick up one of these twos or he can pick up a one. Now, if Alice picks up this one, then Bob will be forced to pick up one of these because picking up one of these is a definite loss. So, game will go on in this way. Or the other thing Alice can do is pick up one of these twos. In that case, Bob will be like let's say Alice picked up this one. Bob will be forced to just pick up one of these. Then Alice will pick up this. Then Bob will be forced to pick up this, and so on. So, yeah, we can't really conclude much from it. I just wanted you to get the intuition that uh, since we cannot pick up the maximum element, maybe try to think about picking up the second largest element. If you pick up the second largest element, like basically by value, one of the elements which is the second largest by value. So if you pick up one of these, then Bob will not really have any choice among the other elements. So if the second largest element is coming up even number of times, then again you can try to think about the third largest element. Right now this is coming up odd number of times, so yeah, it makes sense to pick up one of these elements so that eventually you would be the one to pick up the last one of these and Bob would be forced to pick up one of these elements, right? If the array was something like this, you want Bob to pick up one of these. So and like that if you pick up one of these three elements, then in that case you will be the one who will pick up the last one, and Bob will have to pick up one of these. Or the other thing which can happen is, let's say you chose this two and Bob chose the three, so you don't really need to choose these twos anymore. You can just go on with the three. And probably it should be clear. I think that I still over explained. Was not necessary, I believe. So approach which we have got now is, in the array, the very first thing is the order of the elements does not matter. It does not matter whether the element is 3 1 2 4 or sorry, 3 1 4 2 4, or the array was like 1 2 3 4 4. You know, even if the array is sorted with the exact same elements, the answer will remain the same. Whoever would be winning. So let's just sort the array because it's not changing the answer. After that, you can just easily count the number of times the largest element is coming up. And if it is coming up even number of times, then you will have to check up the number of times the second largest element is coming up, and so on. And at any point, if you find out that there is any element which is coming up odd number of times, then you know that allies can win. And if you try to think more about it, you will actually realize that if there is any element which is coming up odd number of times, then it means that allies can definitely win. Because the only case where allies will not be able to win, while thinking about our approach, is the case where all the elements are having even number of frequency. So if it's something like 1 1 2 2 3 3 4 4 4 4, maybe anything like that. In that case, whatever element you pick, let's say you picked up this 2, Bob can just counter it by picking up the other element, and you will have to now pick up one of these, and eventually you will run out. So this is the only case where allies is losing. So if there is any element which is coming up odd number of times, then allies will win. Now let me show you my approach. Mine is similar to the one which we had been discussing earlier, that we can actually check the frequency of the largest two elements, the largest element, then the second largest, then the third largest, and so on. Uh, During the contest, I could not think of simplifying it to this extent, that just out if there is any odd element or not. So I'm just taking up the inputs, sorting it, and then I have been going through all the elements. Yeah, by the way, I'm sorting it in descending order. Then I've been going up from the largest to the smallest elements, and uh, basically this is just counting the number of elements, the number of times the largest element is coming up, and then like uh, I just sorted the array in the reverse order. And after that, I have been going through the array, traveling through it, and as soon as I find out any element which is different from the last one, uh, at that point I know that I have already, like, it means that I have counted all the elements uh, which were equal to each other. So I can just check, like, I have got their frequency, I can just check whether this is even or odd, and then do the same thing again and again. The way I have implemented it might be looking a bit complicated to some people, but like, what you can do is use that information that n is less than equal to 50 and ai is less than equal to n. So you can just create a count array of size n plus 1, or maybe just call it as 51, whatever. And you can just store the frequency of each and every element and then iterate from 50 till 0 and check out the count of I and so on. You can just do something like this, whichever looks good. The time complexity here is just big of n log n because I have been sorting. So it could have been done in better time complexity, but it does not really matter. The way of doing it in a better time complexity could have been this one, where we are not really required to sort the array. So let's move on to the second problem, array craft. The problem says that we have been given an array B of size m. Sorry, we are not given this array, but we have been told that for any array B of size m, we define maximum prefix position of B as the smallest index I that satisfies this given equation. Similarly, maximum suffix position of B is the largest index I that satisfies this condition. And like we will look at the condition later on. So we would be given an array with three integers, we will be given three integers n, x, and y, where n should be the size of the array which we have to construct, and the array should consist of either 1 or -1, and the maximum prefix position of a should be equal to x, and the maximum suffix position of a should be equal to y. And in case if there are multiple arrays that meet the condition, we can print any of them, such that oh yeah, it can be proven that an array would always exist under under these conditions. And here n can be pretty huge. It can be as large as 10 raised to the power 5. And one thing you should notice is the maximum suffix sum that the maximum suffix position, that is y, is always strictly less than x. And like this thing would be important for us to have a proof that an array would always exist under the given conditions. If y could have been equal to x, then it might not have been the case. I'm not really sure about it, but at least for this case, it's always uh, gonna be possible. We will have to print the array. Now let's look at this. The maximum prefix position of B is the smallest index I that satisfies the sum of elements of array B from 1 till I, from index 1 till index I, that is the prefix of length I, is equal to the maximum possible sum of any prefix. The equation is um, like I is the uh, maximum prefix position of B if I is the smallest index, such that the sum of Bj from j equal to 1 till I, basically the sum of the prefix of length I, is equal to the maximum possible sum of um, any prefix j, and j is equal to 1 till n. Okay, it might be looking a bit confusing, but this equation is saying that for an array, you will say that the maximum prefix position is equal to I if for the index I, the sum you have in uh, the sum you have of these elements, that is the prefix, is actually the maximum possible sum of any of the prefixes. That is what the expression is equivalent to. And the same thing goes for the suffix. There you will be just saying that the okay, so there is one more thing. There is one more way of talking about this position I. You can just say that among all the prefixes, the prefix with the maximum sums, among the prefixes with the maximum sum, like if an array is 1 1 minus 1 1 minus 1 1 minus 1, anything like that, in that case the first prefix is having a sum of 1, then 2, then only 1, 2, then 1, then 2, then 1, then 0, then 1, and what, like whatever. So in this case there are three prefixes. Okay?
Yeah, there are three prefixes, one, two, three.
which are having the maximum sum. So index I will be the smallest one, the smallest index where you're having the maximum prefix among all of them. This is the other way of uh, thinking about the expression. So in this case, we know one thing for sure. Like if you are being given an array, like you are told about the length of the array, and you are being told that the maximum prefix position is, let's say, 3, this one, the index 3, then you know whatever sum of this prefix is, there will be no other prefix with a larger sum. So it clearly means that this value, the value on the index I, must be equal to 1, because if it was equal to minus 1, in that case the prefix without this element would have been having a larger sum, right? Which would be contradictory. So we can easily say that element here must be equal to 1, right? And you know that next element must be equal to minus 1. In fact, you can easily tell that uh, if you go from this point towards the left from here, then for any of these subarrays, their sums must be uh, actually they should be positive. Yeah, they should be positive, because if at any point for any subarray whose like for any subarray ending at this place, let's say this one, if its sum was non-negative, uh, non-positive actually, even if it is zero, even if it is zero in the, like in this case, uh, then removing this, like if you remove this whole subarray from the prefix, you will be left up with this prefix having the same sum. So in that case, this one should have been the uh, maximum prefix position, which would be contradictory because we know that this one is the maximum prefix position. So you know that for any subarray which is ending at this position, the sum of those elements must be positive. It must not be non-negative, or it must not be zero or negative. And same thing will go on for the suffix. Like if you're talking about this guy as the suffix, uh, obviously just ignoring all of this, then you know that the element here must be equal to 1. Otherwise, removing this would have caused this one having a larger sum. So this element must be equal to 1, and this element must be equal to minus 1. And for any subarray starting at this position, its sum must be positive, and for any subarray ending at this index, its sum must be negative. Otherwise, including it could have increased the suffix sum, right? So, like from this, let's simplify the problem for once. Let's say that you just had to create any array where you had been given a condition for the maximum prefix position, and there was nothing, there was no constraint for the maximum suffix position. Okay, so I'm just saying that let's say you had been given that this prefix must be having the maximum sum, and it should be the uh, smallest index I, which is having the maximum prefix sum till now. So how will you solve it? Try to think about it. I hope you tried and could identify that you would like to have all these subarrays ending at this position, like all these subarrays with a positive sum. So why don't we just take 1 1 1 1 everywhere? And you would like to have these subarrays with negative sum. So why don't we pick up minus 1 minus 1? You know, this can be the simplest way of making sure that all these subarrays will have positive sum and all these will have negative sums. Though there can be other solutions as well, like even if you had picked up this as minus 1 and uh, even this as minus 1, even in those cases it would have worked, or don't edit it. If you don't change it, it's also fine. So, and yeah, you could have picked up like you could have kept it as plus 1 also. Even if you had created an array like this one, it would have also satisfied the conditions, right? Now, since we are not having just the maximum prefix position part, we are having two things. You will be told that you want to have maximum prefix position at this place. This is X. And you will be told that you want to have maximum suffix position at this place, let's say. This is Y. So you can't really go exactly in this way because one of them is saying that after this position, we would like to have a -1 here. Whereas this is saying that I would like to have a 1 here. So yeah, for these elements and these elements, uh, both of these are actually willing to have different things. If you are thinking about the maximum prefix position, you are willing to have something like 1 1 1 1 -1. Whereas in thinking about this case, you are willing to have something like -1 -1 1 1 -1. Right. So there is some contradiction for these people, but there is no contradiction for at least some of them. That is this guy, that is this guy, and this guy. They should definitely have one. Like one having one is just making things good for them. So even if the array looked like this, where the uh, maximum prefix position was till this point and the maximum suffix position was here, there is no loss in having all these elements as one because they are just helping us to keep these subarrays some positives, and actually it will help for these as well, right? Similarly, for all these subarrays, their sums will easily become positive. So yeah, we are just sure that having one here is a good thing. But what about the other people? You can't put up ones everywhere. Like you definitely cannot pick up a one here. You must pick up a -1. Otherwise, this suffix will get better if you just put up a one here. And the same thing goes for this element. You must put a -1 here. Otherwise, some of this prefix would get larger than this prefix. Uh, so we don't really have any choices for these elements, and thinking about these elements, it's not a very hard choice to make. What about the other elements? Again, try to think if you can actually make some progress from here. It's not very difficult now, and it's uh, having one edge case even now though. Like not an edge case, but many people guessed it wrong during the contest. Okay, so one intuition which I got after the contest, and I saw that many others had also got it, was just put up -1s everywhere. What's the problem with it? So at least that's what I thought earlier, but later on I realized that if the array is something like this, not this, but let's create a larger one. 5, 6, 7, and two, yeah, let's say that this is the maximum prefix position and this is the maximum suffix position. Then we will definitely put a +1 here, -1 here. And talking about the other elements, you can't really put up a -1 here because if you put up a -1 here, then the sum of uh, yeah, sum of this subarray will actually become equal to 0. And we must keep the sum of all the subarrays ending at this place positive. So one thing is clear that we cannot put up a -1 here. है ना? So like there may be some other good ideas to approach from here, but a very simple idea which I had in mind was that since I had -1 here, I can just put up a 1, then -1, and so on. And similarly on the right hand side, uh, like I can just keep all these elements positive as I discussed earlier because they are uh, like lying in the overlapping region. And after that, on the left hand side on the right hand side, if I just put up something like -1 1 -1 1 and -1 1 -1 1 -1 and so on the right hand side and on the left hand side, it would actually not cause any trouble, because the sum of this subarray, then the sum of this subarray, then the sum of okay, there is no other subarray here. Uh, sorry, no other prefix. Like this prefix are having the same sum, but uh, the prefix with the smaller value is this one, which is actually becoming the maximum prefix, uh, pref maximum prefix position. Yeah, maximum prefix position as we wanted it to become. And the same thing goes for the suffix. This is the maximum sum for any suffix. It is coming up here also. So this is the largest index with the maximum suffix sum. So yeah, y and x are both on the indices where we wanted them to be. And if you took toward the left hand side, after these 1 and 1, like you will definitely have at least two ones, as I said earlier, since y will always be less than x. Yeah. So as we taught, like as we had thought about it earlier, that since y is always less than x, the thing which would be in our advantage here is there will be at least two ones. Maybe I should have just at least two ones. And it means that even if we have a -1 coming up here, the sum would definitely remain positive. Then we are adding a 1, so these two already got cancelled out. Then when again we have a -1, again the sum would definitely be positive and so on. So we will never have any trouble related to having any other prefix with a small index having the same sum. And for all the other suffixes with the, sorry, for all the other prefixes with the larger index, they may have the same sum, but it's not a problem since we only care about the smallest index one. And some similar stuff is happening with the suffix. Coding it is pretty easy. You just have to take up these inputs n, x, and y. I'm having like I'm subtracting them by 1 so that they get converted to zero based indexing. And after that, I'm just putting up all the values from index y to x to 1, and for all the other elements I'm just putting up alternate ones and minus ones like these, and then I'm printing the array. As simple as this. So now let's talk about the third problem, that is mad problem. The problem says that, okay, first of all you can have a read over the problem.
Okay, so the problem is saying that they define mad, maximum appearing duplicate in an array as the largest element that appears at least twice in the array.
Specifically, if no numbers appear in the array twice, the mad is 0. And they have given a few examples that if you talk about the mad of an array 1 to 1, then it would be equal to 1 because 1 is the largest element which is coming at least twice. In this case, mad will be equal to 3 because 3 is the largest element. And in this case, mad is equal to 0 because there is no element coming up more than 1. And we have been given an array of size n. Initially, the variable sum is set to 0. And the following process will happen until all the elements of the array become equal to 0, and we have to find out the value of sum after the complete process. So in the process what happens is we add the value, like we add the sum of all the elements in the current array to the variable sum, and after that we are creating an array b of size n where bi is the mad of the prefix of the array a till the element I, till the index I, and then we are setting ai equal to bi for all the integers I. So it's like, take one example, 2112. If the array is something like 2112, what we will do is, first of all, we will have a variable sum equal to 0, and I can't, yeah, no, it's good. So this is, let's say, the array which we have initially, and the value of sum is equal to 0. So the first part of the process is add the sum of the elements in the current array, or add the current sum of the array to the variable sum. So here the sum of the elements is equal to 6. So sum will become equal to 6. And after that, we will do the second part of the process. So this was the array A. Now we will create an array B where for the first element till this point, what is the largest element which is coming up at least twice? There is no element. So the first element will be 0 in array B. Then till this prefix, how many elements are there which are coming up more than once? Again, no element is coming up more than once. So again, we will have a 0. Then till this point, how many elements are there? There is just one element, that is 1, which is coming up more than once. So this is the largest element you have right now. Then till this prefix, how many elements are coming up more than once? There is just this 2 coming up. Sorry, like there are, this 1 is coming up more than once, and similarly 2 is coming up more than once. The larger one is 2, so you will have a 2 here. Now again, since all the elements are not equal to 0, okay, before that, now what we will do is just copy all the values of the array B to the array A. So now your array A will become equal to 0, 0, 1, 2. And then again we will do the same process. The sum of these elements would be added to the variable sum. So sum will become equal to 9 because the sum of elements is 3. And then again you will create an array B with these prefixes, and we can see that there are no duplicates, so everybody would be 0. Now you will again uh, make A equal to this array, so it will become 0, 0, 0, 0, 0. And since all the elements of the array is 0, we will stop now. So that's how the dry run of the approach is looking like. So uh, the size of the array can be pretty huge, and the values of the array would be in the range from 1 to n. I think in my approach I never used this information, this piece of information. And this piece of information is important because it is telling us that you cannot have something like n square solution. So after thinking a bit about this problem, like during the contest, I had a thought about the problem for quite some time, trying to do some dry run and all on all the sample test cases. I realized one thing, that initially the array might be anything like 2, 1, 2, 4, 1, 7, 6, or whatever. But once both of these steps are done, after this, you know that the array would definitely be sorted, because like, let's build it. You will notice this with me. When you try to create the array B from it, initially the first element is 0 because we don't have any duplicates still here. Then till this point again we are not having any duplicates. Till this point we are having one duplicate. So you will have a 2 here. Now till this position, the value which we would be putting up at this place might go bigger than 2, but it will never be less than 2. We will always have this uh, pair of duplicates. No, we will always have this pair. So, like in this case, who will come up here? We know that the value will never go lower. It might go larger someday. Like let's say if instead of the 7 there was a 4 here. So again in this prefix also you would have only 2 as the largest pair which is coming up more than once, even though you're having two pairs of duplicates now. Then coming up at for this prefix, you are now having 4 in 4 forming a pair. So 4 will be the largest element now, and then when you come up here again 4 will be the largest element. So after simulating this process once, we can surely say that you will have the array sorted. Right. Now the thing is, now we know that the input we will have is gonna be sorted. So thinking about this as the input can make the problem simpler, right? Because it's not a big deal to just simulate what we had been doing here. You can either use a set or maybe a map. I don't. I'm not sure if it is good to do with a set or not. Maybe not possible with a normal set, but you can easily do it with a map. You can just keep track of the frequencies of all the elements till the prefixes, and if you ever find out any element coming up more than once, then you can just set the value of the maximum element till now. Yeah, you don't even need a map. You can do it with a set also, but let's use map for now. At least in my solution, I used map. So yeah, the thing is, we are definitely gonna be having an array with uh, sorted elements, but there is actually it's also fine even now, even at this place. Yeah, let's do one thing. Let's try to solve this problem itself. Like what will happen after this? Your array A will become equal to this. Then you will find out the sum of all the elements here. And after that, you will again apply those operations of the second step. You will again do this whole thing. So let's do it in the array B, or actually the next array A. The first element would be 0, the second would also be 0. That's obvious. But the third element would definitely be 0. Like the first non-zero element would definitely be 0 because it does not have any other element available. So, like obviously it cannot form a pair. है ना? Till this prefix is till this prefix, since there is only one non-negative element, you know this thing for sure that it cannot form any pair because there is no other non-zero element available. After that position, there may be some elements equal to it, and if there are any elements equal to it, they will be coming up all together, like in this case. So you will have 2 here, and then for the next element also you will again have a 2. Then for the next element, this 4, since it is the first element of the group of 4s, it will not have any other element equal to it till the in the prefix till this point. So it would be equal to the element which was coming before it, if it was coming a bit more than once. Like in this case, 2 is coming up more than once. So you will have a 2 coming up here. And yeah, this at the place of this 4, we got a 2. And now for this 4, you have got two 4s together. So you will have a 4 here. And similarly, in the next step, you will now have a 0 at this place also. Then you will have a couple of 2s, and now at this position again you're not having any pair of 4s, so you will have a 2. And after this 0 0 0 0, again at this place you will not have any pairs in this prefix. So you see that uh, after every couple of moves we are having the number of zeros being added one by one. the number of zeros has been increasing, and it is looking like the uh, elements are shifting towards the right from this place. Uh, this element got removed and all the other elements got shifted once. And then again this element got removed and all these elements got shifted once. Now again the same, like a similar thing is happening. This element got removed and these got shifted here. And it will go on until all the elements will become zeros. So to be honest, we have not really used much of our observational skills or anything. We have just did some dry run. One observation here which we have done is that since we would always like for any array, the maximum element which is coming up at least twice in this prefix would definitely be greater than or equal to the maximum element which is coming up at least twice in this prefix, because whichever element is coming up more than once in this prefix would also be coming up in the larger prefix. We used this knowledge of ours, and later on this is sort of an observation which we made, that it is looking like the non-zero elements have been shifted towards the right one by one. And if you think that the problem is done, you're not correct right now, because there is one case which we might miss out, and the case is that sometimes uh, after the first move, like whatever the original array was, after one step being done, it might look something like 2 2 3 4 4 5.
And when you make up the next array, according to our logic, it should have been something like 0 0 2 2 3 4 4. But in reality, it won't be because 3 won't have any pair with it. It would actually look like 0 0 2 2.
Like 0 was 0, 2 became 0. For this 2 we had this pair. For this 3, again it could not have any pair till this point, and then we got a 4. So 4 is also not having any pair till now. So again will get a 2, and then we will get a 4 here and then a 5. So this 3 will actually get converted to uh, a 2. Now, if there is any element which is coming up exactly once, even after one operation, like earlier whatever the array might be, then you got it converted to sorted array, and we are still not able to do the problem with the approach we had got earlier, because some elements might again get deleted, like this one got removed or actually got replaced by the element which was coming up before it. So this approach is not really working well on the first go, and this is where I observed one more thing. After this, when I have created another array, other than the last element, oh sorry, it was 4 here. The element you might have on the last place might be alone, or the element you will have, or the first non-zero element you have, might be coming up only once. Or not even this guy. Uh, yeah, no, the first element might come exactly once, or yeah, it won't come. Okay, so even the first element will come at least once. Uh, yeah, this is something I didn't notice even during the contest, but I'm noticing it now for the third case. See, this was the original array you had. Let me call this as the array A. It might have random elements, anything, like let's say it's having 2 1 2 3 4 3, anything. You converted it to A dash, where the first element got 0, this got converted to 0, this got converted to 2 because of the pair, then again a 2, then again a 2, and then at this place there is a 3 because you have got a pair. So this one will definitely be sorted. Not having a problem right now. Yeah, maybe uh, if we had something like 5 at this place and 5 at this place, then for the last element you would have got a 5 here. So there could have been some element coming up only once, not multiple times, because as soon as it got to become the largest repeating element, like the largest duplicate element in the prefix, in the next prefix you got a larger element which is coming up more than once. So this is possible. But when you go to the next pass, in the next pass, the elements which were coming only once will not be able to exist here, right? So now, first of all, you are having sorted array. Secondly, all the elements which were coming exactly once would be removed. This will happen for sure. And after this, like you can just do some dry run on some random test cases which you generate by yourself. Will notice that the thing which we had observed earlier is actually always working. That the first non-zero element will become zero because uh, till its prefix it would not have anyone else to pair up with. But the exact like the just next element, since it would be equal to it, as we are not having any element which is coming exactly once, uh, we will have that element come up here and it will go on until the end of the array. Or if there was some other element other than this guy, other than these two, so if there was some other different element as well, and that element would be removed and you would have got a 2 here. No. Or even if you had some other element coming up more than once at the end, it will actually look like these people are shifting towards right. It can actually be taken as this. So now the problem is quite simple. Now if you're having something like 1 1 1 2 2 3 3 3 4 and like a couple of zeros at the beginning, like after doing 2 passes or 3 passes, whatever you want, after that if you're having something like this, you actually know what will happen on the next steps. Everything will just go towards the right one by one until this guy will disappear at the end. So counting it is quite easy. You know that guy, this guy which is 1, will actually remain in this array till this point. है ना? It will give its contribution in the variable sum as many times as it remains here, which is actually if it's index in zero based indexing 0 1 2 3, yeah, it's having the index 3 in the zero based indexing. So let's say that this is, we are denoting it by I for now. Then n minus I, like this is the number of times, or basically this is the number of positions where this guy will end up one by one. So we can say that this guy will have its contribution coming up n minus I times in the variable sum, because right now this is here. In the next step, it will come up here, like basically at this place, then at this place, then at this place, and so on. Right. So at all the places, it will come one by one, and every time the variable sum would be incremented because of this guy as well. So this is the number of times this guy will contribute in the variable sum, and it is having the value ai. So this is the contribution of this guy. And in the same way, we can just find out the contribution of each and every element, and that's it. The problem is done. So overall, what I have said about the problem is we had some random array. We just simulated the process which we had been told here once to get a sorted array. We simulated the process once again to get an array where uh, all the elements would be coming up at least two times other than the last element, because the last element might be coming up only once, as its partner might have been removed. But for all the other elements, you can just try to prove it on your own that they must be coming up at least two times. So at this place, you will have a sorted array where all the elements are coming up at least twice. And in that case, we notice that all the elements will be going up, like shifted towards right one by one. At least that's what it looks like when trying to try run the uh, example test cases or any random test cases you generate. And so, like, if there is an element present at this place, it will soon be present at this place, then at this place, then here, then here, then here, and then it would be removed. है ना? So these are all the indices where that element would be present. Every time in all these passes, its value would be added to the sum. So you can just count the number of these elements. That is nothing but n minus I, where I is in zero based indexing. So minus I times this element ai would come. So you can just say sum plus equal to uh, n minus I plus n minus I into ai. Now in my code, I have actually overcomplicated it during the contest. I actually did it in some other way, which was to find out the contribution of all of these ones together. Like what will be the contribution of all of these ones, then what will be the contribution of all of the twos which are coming. Okay, which would be calculated after the second pass where all the elements would be coming up at least twice. Then the contribution of these and the contribution of this guy and so on. So this approach is not really good, but the one which I'm talking about right now is actually a very good thing. And to be honest, I noticed this while explaining itself. Uh, Before starting the solution, before starting the PCD, I was thinking about this solution. But this one is looking better. The time complexity would be, I think, if you're having, like, if you're using a normal map, which would take big of log and time per operation. So whenever you pass through the array, like whenever you are simulating this part, you would be having log n time complexity per operation for every element. So it is like big of n log n time. For the first time you pass through the array, like you do the both of these steps, then again you will do both of these steps, and after that you are just going over all the elements one by one. So it's just big of n time. We are not having the use of any map or anything. This will be the time complexity. So in my code, I took the input and applied this operation twice. I did apply these operations two times, like this. And after that, I have been doing a bit complicated thing, which is not really necessary. Let me just tell you what to do here itself. Let's say if you had a vector of integers, like you are having a vector of integers a of size n, on which you have already done the two time, like you have already done the passing uh, steps two times. So you know that the array will not have any uh, unique elements other than the last element. Now you can just go over to all the elements and say that sum should be incremented by n minus I into ai. That's it. I think it's enough. And yeah, use like just do some typecasting if you're not using a macro of typecasting everything to long directly. Otherwise,
Just do typecasting like this or by multiplying one one LL or like whatever you want. So this is the main idea. For every element you are taking the contribution one by one like this.
yeah, the loop which I wrote could have been written instead of writing both of these for loops. It could have been just 3 lines of code. Now let's move on to the fourth problem. This will be the final problem we discussed today. We are having an array A of size n, which is telling that there is a n by n grid, the ith row. The first AI elements are black and the other elements are white. In other words, note ij is the cell of the ith row and jth column. Okay, so it is telling that either you can say like this, or in other words, you can say that for the ith row, the first AI elements are black and these cells are white, which are the remaining cells. So what we can do is either dye one of the 2 by 2 subgrid uh, as white into white color, or dye a whole row white. We cannot dye a whole column white. Actually, it's making the problem simpler that we cannot make any operations on the column. So it is making sure that we don't really have a lot of things to think about. We are having only these two choices, and we have to find out the minimum number of operations to dye all the cells white. So let me in the problem here also. We are having a matrix of size n into n. Now, uh, for each and every row, we will be told the number of black cells it will have, and all the black cells will be coming up at the beginning. So if the problem says that the array is something like 2146 uh, 0, like it can be 0 also. In that case, it means that for now I am giving it a different color, but it should be black. The first two cells here, then the first cell here, then the first four cells here, then the first six cells here. Unfortunately, I have not drawn the matrix this big. Let me keep this as 5 for now. And then for the last row, we are not having any other column. So now our goal is to color all of these cells white. And the two type of operations we have is we have our just choose a subgrid of 2 into 2 size and color all of those cells white. It does not matter whether there was any white cell in that subgrid or not. All of them will become white. And the other thing which we can do is just choose any row and color all the cells white. So eventually our goal is to color all the cells white, and by the way, all these cells are already white. Already this one is white and all these are white. The ones which were not colored black were white. So that's it. These are the two type of operations we have. Now we don't really know on which elements we will apply which operations, but there are a few things which are quite obvious. Like one of them is It would be an n by n grid for now. I'm not counting the number of rows and columns I've built, but both of them should be same. Now let's say that if for the if there are two consecutive rows which are having two black cells, in that case, like all the other cells are already white. Now, what you can do is you can just apply one operation on them of choosing a subgrid. Okay, and you can just convert them to white. So you will be able to turn two rows into white by just applying one operation. And the other thing is, if there is, okay, sorry, not this pen, but yeah, if there is any row having too many black cells, then it is better to just apply the second type of operation where we just convert the whole row as white. This is gonna be better because it will take only one operation and it will get rid of the complete problem at once. So for a very less number of black cells, like if it was one or two and again one or two, like it should not be more than two. In that case, it makes sense to apply one operation like this. If there are too many black cells, maybe like uh, more five or more than five, in that case, it will be good to apply the second type of operation. Uh, and it is not bad if you think that, like initially, even if you get it in your mind that for any row having three or more cells, I will apply the second type of operation. It's not a bad idea if you get it at once at the initial stage. But we will see that it's not always the best thing to do for the rows with three cells. Like, okay, so the next thing is if I'm having, yeah, if I'm having four black cells, basically till this, if I'm having two consecutive rows having four black cells, in that case, either you can go with wiping out the whole row, which is what we were thinking about, and you might have actually got this idea for that for all the rows with three or more columns, three or more black cells, you can just apply this operation. Or the other thing you might have noticed is that you can actually wipe it out like this also by applying the first operation twice. Now, to be honest, to me, the way of wiping out the complete row was making more sense. At least it was looking better. But it actually can be good in some cases to do it like this. This is the thing which I had missed earlier, and I'm trying to think how did I notice it. Oh yeah, I noticed it via test case. There was this test case which was not working with my approach 2252. Like when I had only noticed all these things and I was just thinking of applying at least that to see uh, where I was just thinking to trying to find out any case where my approach will fail. I saw that this test case was one of them. We're having 2252, 2252, 3424, 3424 as the array. So in the first row, you're having, let me just try it first, 5, 7, I draw it too big, 1, 2, 3, 4, 5, 6, whatever it goes on. As the class is going on, my writing has been getting worse and worse, I think. Okay, so coming back to the idea, the first two cells would be black. Again, 2 will be black, 5 will be black, 2 will be black, 2 will be black, 3 will be black, 4 will be black, 2 will be black, and did I mess up somewhere? 1, 2, 2, 2, 5, 2. Okay, it should have been 3, 4 here. Okay. 3 cells black, 4 cells black. The last one would also be 4 cells black. And now, in this case, one way of getting rid of these cells is you can use one operation here. Let me use a pen here. You can use one operation for these two cells, one operation for this guy. Um, you will nevertheless require two uh, operations for these two. So maybe you can just apply two operations on these two together, or one operation, and then one operation here also, because there are 4 cells and you can't get rid of them uh, easily. So yeah, as I told you earlier, like this thing was actually making sense. It never made any sense to apply uh, this complicated thing, because even if there are more cells, it does not really matter. You can just get rid of them via the second operation very easily. So using second operation was making more sense, at least to me. Yeah, and now even at this place, applying this kind of operations is making more sense. So it is taking 7 operations for like by me, and the solution took 6 steps. So this is where I did notice that my approach is failing somewhere. I tried to think about some case where it would fail, and then I noticed that if I take down this guy, like if I apply one operation here, let me just do it, and these four are now having only two black cells, and I can get rid of these by the first operation and these by the first operation. So I will be able to do, like I will be able to get rid of these 4 rows in only 3 operations, for which I was earlier taking 4 operations here. Right. This is the way in which I got to know about, like I observed this uh, way of dealing up with multiple rows together, where you might have some rows with more than 2 cells colored black. And after this, I just tried to think about formulating it, and then I noticed that, like in the array, if you're having one or two, okay, for now, for using one or two, like if there is any
row having either one or two cells, it does not really matter now, because whenever you will apply the first type of operation, you will actually have to choose two columns together, and choosing these two will never make any sense. Choosing
these
these
two will never make any sense, because you will always have to deal with these first. So to me, it looked like it always makes more sense to consider these two columns same, like these two columns as same, these two columns as same, these two columns as same, and these two columns as same. Because if I want to deal with any person here, I will always if I'm picking up the columns in the first type of, if I'm applying the first type of operation, then I will always have my subgrid coming up like this and not like this, because if I apply an operation in this way, I will still have to deal with the uh, black cells in this column, and if I deal with the black cells in this column, I will have to apply the subgrid on these columns anyways. So it's better to consider these two together, uh, and then these two columns together, then these two columns together, and these two columns together, and so on. So for now, if there is any row having one or two cells, I will denote it as maybe A for now. If there is any row having three or four cells, I will denote it by B. And for any row having five or more cells, it never make any sense to apply the type 1 number of operations, because just dealing with one row, you will have to apply at least three number of operations for that row. It will obviously take out another row along with it, but it is always better to apply type 2 operation twice. So for any row having five or more number of rows, sorry, number of columns, or yeah, for any row having five or more number of cells, I will denote it by C. So you will be given some array. Like now the problem is like you will be given some array having A, B, C, B, A, C, like whatever. It will have a few A's, a few B's, and a few C's. We know one thing for sure. Applying the type 2 operation on C is making a lot more sense. Like I have not really proved it, but to me it is looking very intuitive. At the very least, I can't think of any counter case where this will fail, because if there is some row having maybe five number of black cells, you will have to apply, and if you're thinking about applying the type 1 operation, even if you apply something like this, some operation like this, you will still have to apply some operation like this one and something. So it will take at least three operations, and it will not really deal with three rows. Like in any case, it will never deal with three rows, because there will be something left on the row just coming down. So you will have to apply one operation here nevertheless. And to me, I think it makes more sense to just destroy this row in one operation by using the type 2 method. So at least this is what I am feeling. There, I can't think of any counter test case. So one thing which comes up to my mind is maybe if there is something like this was having two black cells, this was having five, this was having um, maybe again five, and then this was having two. So I could have done something like uh, one operation here, one operation here, one operation here, one operation here, which will deal with four rows and four moves. But again, it is not having any benefit for me, and there is nothing better I can do. Like I can't really deal with, like, in case if I had applied four type 2 operations on these four rows, there is nothing I would get better in this case compared to this one, because applying the type 2 operation will deal with the complete rows, whereas applying the type 1 operations four times is not really dealing with everything. If I had something here or something here, it could have been problematic. From what I can understand, it will always make sense to just apply the type 2 operation on all the ones, on all the C's. And if you ever see a couple of a couple of A's coming up together, it makes sense to just deal with both of them in one operation. You know, as we discussed earlier, like you can deal with yeah, like this case, you can deal with these in one case, in one step, by having a 2 by 2 grid. And for the case if you are having something like A B B A, you can apply one operation in this way for converting the B's to A's, like for converting two consecutive B's to two consecutive A's by applying one operation here. And after that, you can just make combinations here. So if you ever see something like A and then a few B's and then A, and then you try to convert them, and then after having some pairs of A's, making them into two pairs, it is better because it will save us some operation. But as you can see, it will not always be better. Like if you are having odd number of B's, you might not be able to think of a good way of pairing them up, because pairing these people up, you are still left up with one guy, and the only way you can deal properly with this guy is just using the type 2 operation, or using two type 1 operations on these two people, which is not really having any advantage for us. So I hope that you're able to notice if we are having odd number of B's, it's not really giving us any advantage. So as of now, it makes more sense to only consider the case where we are having even number of B's. Otherwise, we are not having any advantage. And in the case wherever we are having odd number of B's, sorry, even number of B's, what we can do is just first of all convert these B's to A's, and like whatever. After that, you can make up these pairs, and it took one operation here, one operation here, three operations here. So it took us up a total of 5 operations for changing these 6 people, out of which two of them were B's. If you had not been applying an operation like this way smartly, in that case, you might have ended up using 6 operations, because you would have maybe applied 2 operations for these two people, 2 operations for these two, and 2 operations for these two, or something like that. है ना? So all I can think of is now, whatever I can think about is that whatever the matrix was, you had some elements like 2, 4, 1, 3, 6, whatever. As we discussed earlier, that you will have columns in pairs. Like thinking about columns in pairs is making sense. So this is something specific to my implementation. I just converted these to um, like seal of whatever element I am having by 2. So if I'm having like 2, it will become 1. 4 will become 2. In case of 1, seal of 1 by 2 is equal to seal of zero point 0.5, which will be equal to 1. So 1 will remain 1. In case of 3, it will again be like 3 by 2 is equal to 1.5, which is sealed, so it will become 2. And for 6, it will become equal to 3. So this will be the new array, like in terms of the new pair of columns. So okay, I just want to check one thing. Yeah, it's recording. I just thought what will happen if recording was not happening. It's like 2:30 a.m. right now. I don't want to start recording once again. Okay, so we are having uh yeah, this is okay. Let me draw the new columns we have, which are coming up in pairs of two twos. So we are having one pair of black columns, then two pairs of black columns. Now, okay, now you see, it does not really matter there, since like there was earlier only one column instead of two columns, but we are saying that there is one pair of columns which is having black cells. Now it does not really matter whether it was completely black or it was only having partial black case, because we would be covering up the complete pair of columns nevertheless. These will be the black columns we have. Now, the type of operation we would be applying is not gonna be a 2 by 2 anymore because we are having a pair together. So it would be like this one. Basically, two adjacent elements, one above the other. Or you can say that any two new cells which are sharing a common horizontal line or horizontal edge or horizontal side, whatever you say. So now how will we deal with it? We know that we should definitely apply the type 2 operation here, and we can't really do anything about it. Applying type 2 operation on these will make more sense, or what you can do is just apply type 1 operations here and type 1 operations here. So that's also something you can do. In any case, it will take 5 operations for us to take it down. And yeah. So how will you decide where to use the type 1 operation and where to use the type 2 operation? Either you can just go greedily, you can just start going from the top, and like you know that for every row you have to remove it for sure. So if the row is having 3 or more value, like the value, if the value is 3 or greater than 3, which means that it is actually a type C row. If it is a type C row, in that case, it always makes sense to apply the type 2 operation. So we know for C we have to apply the type 2 operation. Then talking about A's and B's, if you ever see A coming up together, it will make more sense to apply the type 1 operation on both of these together. If you see
A coming up after B, in that case, there is something tricky you can do. That is like
you know that you will have to deal with this A anyways, है ना? Now, if you see this A, like this is an A itself, I can just mention A, this is B, this is A, this is B, and this is so for a like a case where you see A coming up and followed by B, you know that applying a type 2 operation on A will be just a waste of your resources or operations, whatever you say, because a better thing than applying like taking down the whole row is take down this cell along with the cell just beneath it or but below it. Yeah, the cell which is coming up just below it. You can just take down these both cells together. So applying the type 1 operation on A is the only thing you should do. Like it does not really matter whether you see an A after it or a B after it. You must apply this operation only. It's always better to apply it. है ना? There is no advantage in applying taking down the complete row. Uh, okay, so you can easily say that if you encounter an A, if you encounter an A, you will just apply the type 1 operation. And once you apply the type 1 operation, if the next element which was following it was A, then you can just skip it because it would have also been destroyed. And in case if it was a B, then in that case, you would have got something like these two being destroyed. Then this is remaining, which you must destroy. So you must apply some operation here. Now again, the same thing is happening. applying an operation on this whole row is not making any sense because you are having only one cell here. So it's better to apply it in this way, and does not matter whether the next element is A or B or C. In any case, applying this is better, because if the next element is A or C, it does not matter. If it is um, let's say a B, if the next element would have been a B, in that case it would have been converted to an A, right? Let's say if at this place it was a B and was having this, it was having something here also, but you destroyed it. So now that B would have been converted to an A, because it would have only this much area remaining. So uh, even for this B, you would apply an operation, and now again, uh, after this B, if the next element is either A or B, does not matter because it would be considered as A only. And if the next element is C, it will still be considered as C. So, like we can think in this way, and we can form some greedy approach, and greedy will work. It it will work. One of my friends solved with it. Uh, the other thing which we can do, the one which I applied during the contest was, I noticed that let's say if, since I have to get rid of all the rows at the end of the day, I want to get rid of all the cells, which means I have to get rid of all the rows. Uh, I can say that for every row, I will have to remove all the cells on it. Now, what can happen? Like this row, like the row might have zero number of black cells. By the way, whenever I use the word cell for now, I'm talking about the new cells which I've created. I'm not talking about the older cells. I've just changed the way the inputs were looking up. If you want, you can just deal with these people. It's up to you. So there is a row with zero number of black cells. You don't really need to do anything. You can just ignore it. Um, let's say if the row number was I and it was having zero number of black cells. So yeah, if you were on the ith row and the row was having zero number of black cells, you require zero number of operations. If it had one number of rows, if it had one number of cells, then you have two choices. Either you can apply the type 2 operation, which does not really make any sense, but it will get rid of the complete row for now in one operation, or you can apply the type 2 operation, which might get rid of the next row also if the next row is comprised of A. So if you're having only one row, if you're having only one cell right now, then it does matter what is the next row comprised of. So if it is a case like, okay, I can just actually use the words A, B, C here. So if it was a type A row, oh sorry, yeah, if it was a type A row, you don't really need to do anything. If it was a type B row, sorry, if it was a type B row, you could remove it with, okay, my bad. If it was nothing, you don't really need to do anything. If it was a type A row, you could either get rid of the complete row with type 2 operation, or you could apply the type 1 operation. In both these cases, you would be using one of your operations. And you know that if you are getting an A instead of, like, just let's not just consider the case A, but consider the case if it is an AA, you're getting rid of both of them in one operation. If it is an AB, then like you can't say if you are doing good or not right now. It does matter if the next cells are like this. basically b coming up even number of times and then you are getting an a. In that case, um, how many operations would you require? Let's say that b is coming up x number of times. Then you will be having x plus 2 number of elements, which would require x plus 2 by 2 number of operations to be dealt with once you have made all these elements equal to a. Or maybe let's take it simple. See, if you're having a then a lot of b's, which is let's say x number of times coming up, then you will first of all require x by 2 number of operations to have um, them all converted to a's. And once they are all converted to a, now you're having x plus 2 number of a. So you will require x plus 2 by 2 number of operations to make all of them equal to um, what? 0. Basically all the cells, right? So x by 2 plus x plus 2 by 2 is nothing but x plus 1, I think. Yeah, it should be x plus 1. Yeah, these are the only choices you have. Either you can apply the type 2 operation, or you can take down two a's in a type 1 operation, or you can have multiple b's along with some a's at the corners being taken down in x plus 1 by x plus 1 operations, where the middle ones are coming up x number of times. Yeah, I think that for many of the people, greedy approach might be looking simple. Uh, the one which I applied here is just nothing but dp. I said that I know all the things which can happen. Like at any row, I know all the choices I have. So I just said it in this way that dp of I is nothing but the minimum number of operations required to die all the cells in the first I rows. So obviously the answer will be dp of n when we would have dealt with all the rows, all the n rows, and the base case would be dp of 0 being equal to 0. Like at the time when we have not dealt with any of the rows, cost is just 0, and we want to go from here till here. And the transitions we are having are sort of like dp of I plus 1 can either be equal to dp of I plus 1. Basically, if you apply the type 2 operation, you can always have this kind of uh, a transition. And in the case if on the index I and index I plus 1, you are having the AA wala case, where you are having uh, basically 1 column, like 1 cell. I'm talking about the cells which I have created. So in terms of the inputs given by the uh, code forces jury or like whatever, it would be either one or two cells in both the rows. In this case, you can have a transition like dp of I plus 2 becoming equal to dp of I plus 1. And in the case where you are having a and then multiple b's together and then a, yeah, where b is coming up odd number of times, sorry, even number of times. So if it was index I and it is let's say index j, then you can say something like dp of j plus 1 equal to dp of I plus 1. Sorry, not 1, but the cost of making them blank, like whatever cost it comes out, we already know how to count the cost. Like b is coming up 6 number of times now. So the cost will be 6 plus 1 as far as I can think of. It should be 6 plus 1. uh, because it was coming up as x plus 1 and x is 6 here. So we can just simply count, right? Now, if you ask me greedily, I would say that you can just completely discard the other two options you have. Like you can just completely discard this and this transition and go up with this third transition if you had to pick up one of them. Like it's just a useless thing which I was talking about. Like when you're talking about DP, you don't really need to uh, think which case is better. Just say that we will count out all the possible combinations. And yeah, by the way, the reason I'm having J plus 1 here, just in case if somebody got confused. When I said DP of I was talking about like DP of 2 will say that I'm done with the first two rows, and the index in zero
Based
based
indexing
indexing
for
for
the
the
third row would be I equal to 2, right? So that's why I said that if this is the guy if this is the ith guy, 1, and then let's say there are two twos and then 1. So the indices are 0.
0, 1, 2, 3, 4, 5, and 6. Uh, from there on, I can say that I can deal up with these people in 3 operations. So I would be done with 6 rows. So I will update DP of 6. It is just because the DP state which I have declared is sort of 1 based indexed, and this one is sort of 0 based indexing here. So that's why it might be looking a bit weird to some people, but this is how I am used to, and you don't really need to follow me. You can have your own DP transitions and all your own states. And I would strongly uh, suggest you to try the greedy solution also. Do both of them. So now the third kind of operation might be looking a bit difficult to some people, but I don't think it's difficult in reality because overall, like this transition will happen only when the current element is actually equal to 1, and the time complexity would be dependent upon the number of twos you see in front of you. So at some point of time, you might be spending, like you might be having a big loop to find out the next occurrence of 1 after having some twos in between. One thing you can do is just uh, use some set, or maybe just create an array which with the help of which you will be able to keep track of the next occurrence of 1, so you don't even have to apply a for loop. But even if you apply a for loop, you see for all these elements you pass on in the middle, for all those elements you will not have to apply that for loop. So overall, asymptotically, you will have a big of n time complexity for the transitions over all the states with this kind. And for the other transitions, they are already pretty simple, like this one and this one. And to be honest, you don't really need to take care of this case because this AA wala case is a special case where B is coming up zero number of times in between, right? So even if you don't apply this directly and you just take care of this transition, you will still be able to cover up this case in like it will be covered in itself. So uh, yeah, I think that's it. If you know about DP, you should probably be able to solve it on your own now. And I will show you my code, but it will definitely look a bit different from what people generally write. After taking the inputs and changing the value of AI to seal of AI by 2, which can be changed in this way, I created an adjacency list for DP, which was completely not required. It could have been avoided, but I just thought that what's the problem in it? I just used it directly. Yeah, basically this could have been avoided, but I just was a bit uh, like willing to play safe, so I did not uh, apply for loops inside this for the special case. Instead, I just created an adjacency list which will keep track of uh, all the transitions and their costs. Is looking a bit similar to graphs. In my case, I actually relate DP with graphs, so that's why I'm used to this kind of thing. And after that, I just applied a normal DP. So I would suggest that ignore my code and try to write it on your own. If you want, you can maybe look up at the codes written by Tourist or Jiangli, because they generally have very nice quality. And yeah, simply ignore mine. So I hope that you like the video, and tell me in comments whether you enjoyed, whether did you learn something new or not. And if you felt that I was not doing something good, please mention it in either the comment section or the feedback form. It's up to you. And even if you feel it good, even if you feel the video was good, you can still mention it in the feedback form or the comment section. I would be happy to see it. And thank you for watching the video. Bye bye.